If the length is equal on every side, say it's equilateral like this roadside. And since every angle's less than 90 degrees, an acute triangle it will also be. If you add up every angle, there are 180 degrees in a triangle.
Well, hey there, geometry students, and welcome back into Chapter 5. This is 5.3 of the Big Ideas. We're here proving triangle congruence by SAS in this lesson. So SAS, which is S stands for side, A stands for angle. So we're going to be using this side angle side congruence theorem to prove triangles congruent. It is one of four of the S and A ways of proving triangle congruence. So we're going to see three other ones, including this one, that also use sides and angles. And there's also a fifth one that doesn't use sides and angles. It's for only right triangles. But this side angle side can be for any of the triangles that we have. So that could be any of the acute or even obtuse angles that we have, triangles we have. All right, so let's go into our cartoon for our day. So, trouble in paradise for the Michelin Man. And the wife put down a spike strip on his side of the bed. I guess he needs to get the hint. Not sleeping there tonight. All right. So, Michelin Man apparently got married to the Michelin Woman. All right, so on page 135, we see the theorem here for the side angle side congruence theorem, SAS for short. And so what we're talking about is if we, basically it says if two sides and the included angle, so that's why the angle's in the middle, the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. So here you have like triangle ABC, so it shows you that you have, this is congruent here. The 1 mark is congruent to the 1 mark for DE. The 2 marks are congruent here, so A to C and D to F are congruent. And so the angle that's in between those 2 marks is also congruent. Angle A is congruent to angle D. So if that's true, you have a side angle and a side of one is congruent to a side angle and a side of another. Then you can just say that the two triangles are congruent. That's all you need. You don't need all of them, all angles and all sides to show they're congruent. Obviously you can have that, but you only need these three, and that would prove that your triangles are congruent. Alright, so let's go ahead and watch this proof here. It's given this diagram here, and it's given that BC is congruent to DA, so that's what the marks are here showing you. And it also is given that the BC is parallel to AD. So BC here has got the parallel marks. These little arrows here show it's also parallel. And you have a line going from A to C, which would be considered a transversal. So we don't want to forget about those things that we've learned in the past. So that would be a transversal with parallel lines. We have some angle relationships that we can do here. It says prove that triangle ABC is congruent to triangle CDA. So ABC, the top one, is congruent to CDA, which would be the bottom one here. So the first thing is we can obviously say the given, right? That's our first thing to do, is our given. And the first given there would be the sides of BC and DA are congruent, and that is a S for when we're trying to build side angle side. That's an S that we can use. And then we also see the next thing is we have the parallel lines are given, so we'll just state that, and off of those parallel lines, based on that, we then can say that because of alternate interior angles theorem, that would be inside here, these two alternate interior angles, that these are congruent. Okay, so here's some angles that are congruent. We could say these are congruent to this one, or this one's congruent to that one, either way. So we can say this one, I would say probably this one here is congruent to this one here. That would give you an A, so we now have an A. So S and an A, we need another S. So if we have, basically if we have this side and this angle, we need to have this side here showing congruence would be AC. needs to be congruent to the AC of the other triangle, which would be true because AC is obviously congruent to AC, or CA you could call it, because of reflexive property. It's congruent to itself. And so there's your other S, so SAS. So now we would say the proved part here, which is the triangles, that those are congruent because of the SAS, congruence theorem. So that's all we needed to do to be able to prove that those two triangles were congruent. All right, so here on page 136, we have our first extra practice. It is a proof. So it has the two triangles over here is in the diagram. So we're looking at these two triangles that we're trying to prove congruent. So that's kind of what you want to see. What are we trying to prove here? And that's that ABD is congruent to triangle CBD. So ABD is the one over here, and CBD is this guy over here. So we have two things in our given, that we have some perpendiculars, that BD is perpendicular to AC. So this is perpendicular, shows a right angle right there. And that AD is congruent to CD. It shows the little marks even in there. So let's start with our givens then. So our first thing is to write down just one of the givens, and that's the one about the sides being congruent. So AD is congruent to CD. So write that down first. And that would be a side. So we have a side congruent here. So that's a S from our SAS. We're trying to use SAS here on this one. The second given here is that we have the perpendicular. So that's another given. So we can just write that down as the given. So that fills in all the givens then, and now at this point we have to go off of this. So off of the fact that you have this being perpendicular, so that this side is a right angle, so that means this side's also a right angle, so that means these two angles here are congruent. So we can say angle ADB is congruent to angle CDB. So that's what we would say here. So angle or BDA, doesn't matter. They said BDA, I said ADB. It's either way, as long as D's in the middle. So they said angle BDA is congruent to angle BDC. So that would be these two angles here, and that is just that they're a linear pair perpendicular. So they are a linear pair because they're right next to each other, and it's perpendicular because that means both of them are 90. So that's just a reason for that. And so that would be our A here. So now we have an S, now we have an A. So SA, we need another S. So to figure out, okay, what S do we need? Do we need this S up here? Do we need this side? No, we would need it to be where the angle's in between the two. So we would need this side right here, BD. Since it's a shared side, that makes it pretty easy because BD is congruent to BD. It's congruent to itself because of the reflexive property again. And so that's our other S, SAS. We can now just write down this proved part, which is the two triangles are congruent. So triangle ABD is congruent to triangle CBD because of SAS. That's what we say over here, SAS congruence theorem. So the main thing there is just to say SAS, really. All right, so let's go on to our second one, which is another proof. All right, so problem number 2, here we have two more triangles that we're trying to prove are congruent. So again, look at the prove part and see which two triangles you're trying to prove congruent first. So J and K, so we have J, and then N is here in the middle, K. So we're looking at this triangle right here, that's congruent to M and L. So M and L, this one over here. So we're trying to prove that these two are congruent. So really this chart down here, we're not looking at that at all. We have a couple of different triangles we could see here. We could see this one and this one as well, but they didn't want us to prove those two. They wanted us to prove the ones on the top up here. So they do give us some givens here with some congruent sides. In fact, JN is congruent to MN. So it shows us the congruent marks right there for JN and MN. And then also NK is congruent to NL. That's these two down here with the 2 marks. So these NK, or KN and NL right there, those two are also congruent. So that's 2 sides right there. And so that's what we're going to start with the given, is that we just start by putting those down. We can just write one at a time. I mean, we could write both of them, but I think one at a time actually kind of is helpful because we can see, okay, here's one right here, it's a given, and that's a side that is congruent. So we have a side already for our SAS. We're trying to use the SAS in this lesson. Eventually we'll have 4 of them to use, and any of those 4 would work. But right now, so far, we're only just learning just the SAS, where A is in the middle. And then our second given, there is another side. So again, just put given down for your reason. And that's another side. So we have two S's. We need another A, but the A has got to be in the middle or in between. It's called an included angle. So the included angle would be right here. This angle is what we need. Here, I'll even mark that off for us. We can see it here. So this is the angle that we need here. These two angles need to be congruent because that's the one that's in between the two sides. Here's your first side, your second side. Your included angle is the one there in between. So right now we don't need this one. We don't need this one up here. We need these to be congruent. And so that's what we're looking at next here. And we can see that they are right there. They are vertical angles. We know that when we see an X. Whenever we see an X like this in any diagram, we know we have vertical angles. So what we can do is just say that those two angles are congruent. We can use the J and K. So J and K, that angle is congruent to MNL. MNL. So you have to name it correctly. We learned how to name angles back in, I think, chapter 1. So naming it correctly, and that is vertical angles, because it does form the X right there. As we can see, those are vertical angles. So vertical angles are always congruent, and that's our other A. That's the included angle. So now we can just say the prove part, put this part down here on our statement, which triangle JNK is congruent to triangle MNL because of not SSA. Remember, it's still going to be side, angle, side, still SAS, even though we kind of got them first the two S's and then the angle, but it's still going to be written down as side, angle, side, because the angle is in between the two congruent sides. It's side, angle, side. All right, so here's our joke of the day. Why does Humpty Dumpty love autumn? Because Humpty Dumpty had a great fall. All right, so on page 137, we see problems 3 and 4. It says, use the given information to name two triangles that are congruent. Explain your reasoning. So in this diagram, we have a circle, center, there's P, and really we only have two triangles here, so these are the two triangles that we would have to say are congruent. There's really not any other triangles in this circle at all. Now it does tell us something here. It says in this number 3 that the angle EPF is congruent to angle GPH. So it tells us right there and shows us even on the diagram that those two angles are congruent. Also tells us that P is the center of the circle. So if that is the center, it's not just some other point, but it definitely is the center, then what we have here from P to E or P to F, these are all going to be radiuses. So you have a radius here to E, you have a radius to F, you have a radius to H, and a radius to G. So that's true. Then all of these are congruent to each other. They're all radiuses, so they're all exactly the same length. They're all congruent to each other. So if their lengths are equal, then their segments are congruent. So now we can definitely see a side, an angle, and a side of one triangle, side, angle, side. And so using the SAS, from SAS, those two triangles are definitely congruent. So here's what we would say then. So we would say right there that triangle EPH is congruent to triangle GPH. You're going to write that part down for sure on this. And then the reasoning, it says explain your reasoning, and here is the reasoning, and it is what I just went through. It says because all points on a circle are the same distance from the center, so all these segments are congruent. PE and is congruent to PG, and PF is congruent to PH. It is given that the angles here are congruent to each other up here, so that the triangles are congruent because or by the SAS congruence theorem. All right, so it looks at number 4 now. It says that this is a regular hexagon. So a hexagon's got 6 sides. There's 6 vertices here from A to F. So it's a regular hexagon. Regular means that every side is exactly the same and every angle is also identical. All the angles are exactly the same inside of here. That's what a regular anything really is. So even just a regular triangle would be the equilateral triangle. Equal angular and equilateral is really a regular triangle. So if that's the case, then based on here we see some triangles formed. Definitely some similar triangles at least look like this right here, like ACF, this triangle, and DBE, that triangle there, look like they could be the same. So we want to go off of that and start looking at this. So if I went from basically E to B, from one vertice to the other vertice straight across, and then this one here is F to C, same thing here, from F vertex C straight across to C, those are congruent to each other. Actually, first of all, I'm noticing this. The sides are all congruent, so I can say even on this triangle, these two, from A to F and from E to D, those are congruent to each other. And then these ones also straight across, from C to F and E to B, or B to E, those are also congruent to each other. So that gives me two sides. So what angle would I need then to be congruent? So I would need this angle here to be congruent. That's the one that's in between side 1 and side 2 on this triangle. And this one here to be congruent, that's the one in between 1 and 2 as well. So those are congruent. These are congruent because this right here, if this is one angle that's all the same, these are all the same, exact same measure on all of these, this is going to go right through the middle of this angle. Same thing here, this is going to go right through the middle of this angle. So this is really an angle bisector. And so if that's bisecting, then this angle is the same as this angle. We can definitely say those are congruent. And so that's now how we can say, using the SAS, that these two triangles are congruent. So here's what we would look at. So you definitely need to write down, I should say, oops, let me get that there, like there. So definitely going to write down triangle ACF is congruent to triangle DBE from what I highlighted. And here's all the reasoning. It says because the sides of the regular hexagon are congruent, so that means that side AF is congruent to side DE, side CF is congruent to side BE. Also, because the interior angles of a regular hexagon are congruent, that's what I said, they're all exactly the same, and CF and BE are angle bisectors, that would be these guys here, angle bisectors, then that means that angle F and angle E respectively, or you're bisecting those angles respectively right here at these two spots, F and E. So that way we can say angle AFC, that's on this triangle, AFC, that was this one I marked off here, is congruent to DEB. So DEB is this angle I marked off here, so it definitely shows that those two are congruent. So then we can say by SAS, these two triangles are congruent. That's what we're saying. These two triangles are congruent by the SAS. So all of that is like the explaining. So it's kind of like a proof, but more like in a paragraph. So real quick, I just wanted to show you this one that's talking about this barn. And he has this picture. It says you're making a canvas sign to hang on a triangular portion of the wall, of the barn wall shown in the picture. You think you can use two identical triangular sheets of canvas. And here's what you know. You know that the RP is perpendicular to QS. That's right here. That forms a 90-degree angle. And that PQ and PS are congruent. So you got the congruent marks there. It says use SAS congruence theorem to show that those two triangles are congruent on each side. Now we did one just like this that had this right angle, so because that's a linear pair and perpendicular, that means that both of them are right angles, so there's another angle. And then RP is congruent to itself, so there's your other side, so side angle here in the middle and this side here would show that, and that's what basically it's going to say down in here. So I just wanted to show you, looking at the actual picture of the barn, that's a kind of a real life situation. Alright, so here on number 5, our last problem, a quilt is made of triangles. Here's what you know. You know that side PS is parallel to side QR. So these are parallel, and you also know that PS is congruent to QR. It says use SAS congruence theorem to show that triangle PQR is congruent to triangle RSP. So first, let's find out, okay, what triangles are we talking about in here? I'm going to go ahead and highlight this. So PQR, so looking at PQR, that's this triangle right down here. So that triangle is one of the triangles. And then the other one, I'll do orange, is RSP. So RSP is going up this way, RS to P. So this one right here as well. So those are the two triangles that we are talking about and discussing. So at that point, all right, so let's mark these off here. So we know that these are parallel. PS and QR are parallel. Let's put some parallel marks on that. So those two are parallel there. And we also know that they're also congruent. PS and QR are congruent as well. So let's go ahead and put the congruent marks in there also. And then we do need to show using SAS congruence theorem. So we need to know another side. So we have one side already given to us. We need to know another side. Well, since they share the PR side right here, PR is congruent to itself, we can then just say, well, that right there is going to be congruent to itself. We know reflexive property would tell us that. And we need an angle, and it has to be the one in between. So it has to be the one over here and the one up here. So the one over here at R on this side for like the yellow triangle, and the one up here at P on the kind of orange triangle up here. Those are the ones that have to be congruent. And since these are parallel lines, this is a transversal as well, and because of alternate interior angles, we know those are congruent. Something we learned back in chapter 3, alternate interior angles are congruent. So we can say right there, those ones are congruent. So let's go ahead and write down everything we know then, and it would build our SAS. So we could start with the first S, and that would be what's given to us here, that side PS is congruent to side QR. That is the given, so we'll want to put down given for that. That's kind of our reason and explain. It says show this, so we want to show based on reasons as well. So it is still kind of like a proof. We have our angle that we know here, so the angle is here. We want to label this or name this properly. So for the angle, we're going to name it this way, QRP, so QRP, this one on the yellow, and then corresponding would be SPR on that orange part, and the reason for that is because of alternate interior angles. Those are congruent. And the last S, so our last S for building the SAS is going to be the side here that PR is congruent to itself. PR is congruent to PR because of reflexive property. And so that's what we need to say. That's showing that those two triangles right there are congruent. Let's use this to show that these two are congruent. And so again, here's a whole explanation as well. You can look through this and see technically what did they exactly say, but they said pretty much what we said. I just wrote it out like this, more of in bullet points like SAS, and there you go. All right, so that concludes our lesson here on 5.3, and we'll be seeing you again on the 5.4 lesson.